All right, so last Thursday we talked about reactions at the benzylic position. We said the benzylic position is that carbon that's immediately attached to a benzene ring, right? And we said you can do normal oxidation, and when you do oxidation, you have two options. You can use chromic acid or potassium permanganate, and it's a very strong oxidizing reaction, which means you always overshoot to the carboxylic acid. The key takeaway from this, though, is it only works if you have benzylic protons. So it doesn't work if you have a quaternary carbon at that benzylic position, because then you don't have protons. All right, so we looked at some examples and we related this to alcohols. We said same thing with alcohols. If you don't have protons, you can't oxidize it. Same's true with benzylic carbons. What's interesting with this is if you've got extra carbons added on, you actually lose those in the reaction. So we went through an example one where we saw an isopropyl group or an ethyl group can be converted to a carboxylic acid. All right, so now we need to switch gears a little bit and talk about new reactions. And let's talk about free radical bromination. And this actually is linked to our pod that we did yesterday, where we said, all right, if you've got a benzylic carbon, so we'll use toluene as our example, and we want to add in a bromine onto that benzylic carbon, we need to choose a reagent that can do radical halogenation. And we know it's similar to the allylic radical system that we saw previously, so NBS and heat works well in this situation. So it works for radical allylic halogenation or radical benzylic halogenation. Either one works. The nice thing with this is once you have this on here, you can do SN2 chemistry, right? So you can have a nucleophile, swap that off. You can turn this into a Grignard. You can do a lot of different things with this once you have that halogen on there. Halogens are really versatile building blocks in organic chemistry. I'm not going to go over the full mechanism because it's actually the same as the chapter 11 mechanism. So make sure you go back and review the mechanism if you are rusty at all. We're not going to spend lecture time on it though. Does that make sense? All right, the neat thing with this sort of halogenated system is you've got a lot of versatility with it, like I said. So let's take a look at some of the substitution chemistry. So go all the way back to first term. And if we think about benzyl bromide, which is this material we just made, we can convert this to benzyl alcohol, where we have an alcohol coming off instead of the halogen. And we can do this actually two different ways. The first way is through an SN2 route, like we mentioned before. And what reagent would we need? NaOH, right? We need a strong nucleophile. However, even though this is a primary carbon, it can also do SN1 chemistry. And why is that? It's a good leaving group. One of the other important things with SN1 chemistry is your carbocation stability, right? That was the number one thing we looked at. Why is this primary carbocation so stable? Because of resonance, right? So what sort of reagent would we need for this? Water. So we just need a weak nucleophile. So these are really easy to work with. They're easy to change into new functional groups. Once we have that alcohol on there, we can oxidize it, make a carboxylic acid. We can oxidize it to an aldehyde. We can tosylate it. We can do a lot of different things with it. So there's a lot of options available. All right. We can also do elimination chemistry. So we'll go back and review this a little bit. And elimination chemistry is pretty straightforward. So let's say I have this compound. What would this be called? Chicken foot benzene? No, isopropyl benzene, right? So we've got isopropyl benzene. What if we ultimately want to do elimination and make this compound. How could we do that? I'll give you guys a minute to think about this, but check with your neighbor. It may take more than one step to get from our starting material to our desired product, but check with your neighbor. All right, another show of thumbs. Who thinks they got it now? All right, so let's take a look at this reaction. Can we do a direct elimination and do this in one step? No, you can try, but it won't work. What are we missing? We need a leaving group, right? So let's add on a leaving group. We can say, all right, MBS and heat. It's a good way of adding on a halogen onto the benzylic position. Whoops. So I'll add on a bromine right there. And then once we have that, how can we get to our final product? Yeah, in this case, does it matter whether or not we use a bulky base or a non-bulky base? As long as it's a strong base, it's going to do elimination. We don't have to worry about Hofmann versus Zaitsev here. So any strong base will work for this reaction. So I'll just pick one. I'll just say, all right, NaOH could work for this. The other kind of cool thing with this is, let's say we want to do the long route. I could actually treat this with water first. When I do this, is it going to be an SN1 reaction or an SN2 reaction? Be an SN1 reaction. So I'm just going to write down SN1 down here. This one up here we did E2. All right, once we have that alcohol there, we can actually convert this alcohol to the same product. And what reagents would we need to do that?
Catalytic acid.
Yeah, catalytic acid and heat. So for example, you could say H2SO4. This is catalytic and heat. And would this be an E1 or an E2 reaction? Would have to be E1, right? Because we don't have a strong base at all. So this would be an example of the E1 chemistry. In fact, this is the same sort of chemistry we saw when we did our formation of cyclohexene from cyclohexanol, right? Anytime you have catalytic acid and alcohol, you can do elimination with it, but it'll be E1, not E2, assuming it's a secondary or higher alcohol. All right, so we've got a lot of different reactions that we can now use in conjunction with the reactions we learned previously. If you want, you can actually go back to your reaction map and add in quite a few arrows. This is just a sampling of all of the new reactions we've seen. So for example, we can now halogenate the benzylic position. We can then do substitution chemistry, and then all of those alcohols can be derivatized. We can oxidize it to a carboxylic acid from any benzylic carbon that has protons. And then once we have a carboxylic acid, we can do reduction chemistry, things like that. We can do a lot of variations of SN1, SN2, E1, and E2. We can derivatize the alkenes or the alcohols. So there is a lot that we can do with these. What we're going to do if we have extra time today is practice some of these synthesis problems. I feel like it makes more sense to actually do practice problems than to just see a chart. Make sense? All right, one last reaction for second term organic chemistry, believe it or not. Reduction of aromatic compounds. All right, so let's do a little bit of review. What is this compound called? Styrene. All right, if we have styrene and we want to convert it to ethyl benzene, what reaction conditions do you think we need?
H2 and palladium.
Yeah, we need hydrogen gas and palladium on carbon. And really what we're trying to do is reduce that alkene there, right? It is a conjugated alkene, so it's not like a normal alkene, but we can reduce it because we're not breaking aromaticity here, right? The aromatic ring is still intact. So that doesn't require very much. In fact, this can be done at low or moderate pressure. All right, and then if we really want to get fancy, we can actually reduce the entire aromatic ring system and get ethyl cyclohexane. However, in order to do this, we need 3 equivalents of hydrogen. We need a special nickel catalyst. And typically this is done at really high pressures, upwards of 100 atm. So most labs won't touch this at all simply because they don't have the equipment to handle a reaction at 100 atmospheres, right? That's really, really, really high pressure. All right. So typically we don't see a full reduction of aromatic compounds. However, we can do a partial reduction. And this is known as the Birch reduction. And so we don't take it all the way to the cyclohexane, we instead reduce one of the double bonds instead. And in order to do a Birch reduction, you first need an aromatic starting material. And then you treat it with elemental sodium. So it's sodium with that not sign, meaning it's a metal. You run this in some sort of alcohol solvent like methanol. Sometimes you even see ammonia used. It doesn't matter too much. And oftentimes you see it as a mixture of methanol and ammonia. And when you do this, like I said, you can reduce it. And what's interesting about this is the reduced product has sp3 hybridized carbons on 2 ends. All right, so the mechanism for this, do you think it's going to be a radical mechanism or a non-radical mechanism? Radical, right? Because sodium's got 1 electron. It wants to give away that electron really, really badly. Okay, so let's take a look at the mechanism. Okay, the mechanism's fairly straightforward. So first step, we know sodium has 1 electron, so it wants to give that 1 electron to one of those carbon positions. Remember, whenever you show electron pushing arrows with radicals, you want to show a single barbed arrow. And when this happens, it's actually going to steal one other electron. Let me zoom in a bit. It's going to steal 1 electron from this neighboring pi bond, like that. And then the other one will hop down here like that, steal 1 more from this side, and then go all the way down to this side. So there's a lot of arrows involved in this. I'll zoom back out. But you can tell there must be a lone pair at the top, right? Because it stole 1 electron from sodium, 1 electron from that adjacent pi bond. We formed a new pi bond on the side. And down here, we must have 1 unpaired electron coming off the bottom right there. This top carbon, therefore, must have a formal negative charge on it. And sodium must be the countercation. Okay, in the next step, what we're going to do is treat this with our methanol, which is a really, really, really weak acid. However, carbon with the negative charge is very reactive, so it will pluck off a proton from methanol. All right, now at this point, you have 1 unpaired electron on the bottom. I'm not going to show the proton on the top because we don't need to in bond line structure. And typically this is done with excess ammonia. I should say it is always done with excess ammonia. So the sodium, or sorry, excess sodium. So the excess sodium will donate 1 electron. You'll end up with a lone pair down at the bottom. And what do you think happens next based on what we've seen previously?
Another protonation.
Yeah, another protonation with methanol. So this negatively charged carbon will steal a proton back. And you end up with your final product. Does that make sense? All right, the trickiest thing with this reaction is determining which carbon in this very first step right here gets that electron from sodium. It's not always immediately clear, so I'll show you guys some tricks for determining the first step of this reaction. So we need to talk about regioselectivity. All right. So let's take a look at a couple of examples. The first one, I'm going to start out with this aromatic ketone. What's that called? Acetophenone. You can't just mumble your way out of that one. All right. So now the question is, when we treat this with sodium and methanol and ammonia, which product will we get out? Will we get one where the double bonds are going up and down? Looks like this. Or will we get one where the double bonds look kind of diagonal, like this? And it's not always immediately clear, but I will give you a hint. Do you think this group, the ketone, is electron withdrawing or electron donating to that aromatic ring system?
Withdrawing.
Withdrawing, right? We know carbonyl groups, if we look at it, can steal electron density. I'll just do a partial resonance arrow pushing. It can steal electrons all the way up to the oxygen. So you see how the electrons are being pulled out of the ring system? That means it must be an electron withdrawing group. Oops. All right, so let's keep that in mind. We'll say, okay, this is an electron withdrawing group. Okay, that means that this carbon, I'm just going to label it in red right here. Does it want electrons or does it not want electrons? It wants electrons. In fact, it's having an electron density pulled away from it, right? So I always remember it that way, is electron withdrawing groups means that the carbon directly attached wants electrons. Okay, so it wants to be reduced, right? All right, so looking at our products, which product had that specific carbon reduced? Would it be the left carbon, or sorry, the left product or the right product?
Right.
What do you guys think?
If it wants electrons, you won't have a pi bond X.
So let's go backwards, right? Another way of viewing reduction is gaining electrons or gaining hydrogens, right? When you gain a hydrogen, that's also a reduction. So when you think about reducing an alkene, you're gaining hydrogens, but it's an overall reduction. All right, so which of these was the reduced product for that carbon?
Okay, the left.
The left one, right? So when we look at this reaction, we only get this one. This one is not observed. And like I said, the easiest way to tell is this carbon right here was reduced. If you really want to get fancy, you can also find the oxidation number and double check to make sure that it was reduced, but you can always remember if you gain hydrogens, you're getting reduced. All right? So let's do a second one. Let's say we've got this starting material right now. What is this starting material called?
Methoxybenzene.
Methoxybenzene, what's its more common name? Anyone? Anyone? Bueller? Anisole. Anisole is the kind of weird name. Some people call it methoxybenzene. Most people call it anisole. Okay, so we've got this as a starting material. Same situation. We can say, all right, with Birch reduction conditions, are we going to get a product where your double bonds are up and down, like this? Or are we going to get one where the double bonds are kind of diagonal, like that? What do you guys think?
Right.
So let's go backwards again, right? Say, is this group, whoops, is this group, the methoxy group, electron donating or withdrawing?
Donating.
All right, let's think about it, right? The first one, we invoked resonance. And we said when you do resonance arrow pushing, you're pulling electron density out of the ring for acetophenone. How about this top one? Can I, for example, do this and say, all right, I'm going to pull electron density up. Nope, not without violating the octet rule, right? However, what I can do is do the opposite and say, actually, I can do arrow pushing where instead of pulling it out of the ring, I can push it into the ring like that. So there's resonance structures where you can dump more electron density into the ring. That means this must be electron donating. This is going to be a big theme in next term as well. So this is electron donating. And that means this carbon right here does not want electrons. All right, so knowing that, which product's going to be more likely, the product on the right or left? Right. On the right, okay? So we can say this one is going to be our desired product. This one will be not observed. Does that make sense? It's a little bit weird to think about. Next term, we're going to do a lot with this electron donating withdrawing thing because it has a huge impact on regiochemistry with aromatic systems. All right, you guys want a challenge?
Oh, yeah.
All right, at least Tim's on board. Challenge. All right, for this one, I want you to first determine the regiochemistry of your product and then have a full mechanism accounting for its formation. Okay? All right, so before we do the mechanism, let's identify the groups as electron withdrawing or donating. So for example, up here, what is that again? Okay, so I'll just write EWG for electron withdrawing group. All right, what about this one over here? Donating. Okay, so I'll write EDG for electron donating group. Okay, so if we think about this carbon right here, on the top, does it want electrons? Yes, it wants electrons. All right, and then we could say, all right, down here, this one does not want electrons, right? Because it's already electron rich. Okay, so looking at our final products, which one do you think makes the most sense? The left or the right? Left, right? Because if we think about it, this one up here has gained electrons, it's been reduced. This one has not changed at all. It's still sp2, hasn't been reduced at all. So that means this one's definitely going to be the better product. This one over here would not be observed at all. So now we've got to do the full mechanism for this. Okay, so let me fill this all in. And we'll zoom in now and say, all right, we've got sodium here with its unpaired electron. We know it's going to kick electrons over to that carbon. Sorry, let me redo this. Some of them are going to go over here. And the last one's going to go down there. So we've got this full cyclic system. It should, sorry, let me do this a little bit better. It's going to the carbon right on the benzene ring. I know this isn't the clearest that it can be, but it's going to the red carbon that we know wants electrons, right? Okay, so now we've got almost to our final product. We've got a lone pair up here, got an unpaired electron down here, still have our substituents coming off. And then in step 2, we know we can steal a proton from our solvent, which in this case is methanol. We still have a leftover electron down below. So sodium can donate its remaining electron.
That's a Benzylic?
Oops, thank you. It's habit. It's hard to break. Here we go. So we'll add in one extra electron. And then last but not least, we have methanol around still, our solvent. So this can steal a proton back from methanol and give us our desired product. And there you go. Last mechanism of second term organic chemistry. Feels good, huh? All right, we still have about 10 more minutes left of lecture time. I did want to tell you before we move on, though, that I posted the full practice exam. Our exam 3 is on Wednesday. Tomorrow, what we'll do is exam review and maybe some synthesis problems. We don't have lab this week, so tomorrow I will be available after class just for kind of small group study session for those of you that do have questions or want to go over any book problems or practice activities. Make sense?